Hello. Okay, today we're gonna do experiment 74, Schmitt trigger circuit. So this is coming from Radioshack Science Fair 130-in-1 Electronic Project Lab. Again, experiment 74. Okay, let me just zoom un poco. All right, that sounds good. I'm going to briefly describe this circuit and then we'll go to the bench to see what you're supposed to see. Okay. So this is like 68 is the, it's called the inverting input, the minus. 69 is the non-inverting input, the plus. 67 is the output. 6370 is the power supply. And here the LED are just there to as a visual aid to understand what's going on. But the idea is that first the experiment is that it's gonna use the op-amp as a comparator, and I already made a video about this, so I'm gonna put a link to that video right now. So first we're gonna use it as a plain comparator, and then we're gonna use it as a Schmitt trigger. Okay, so that's why you have the key here. So when you use it as a comparator, you don't have that feedback loop here. But I'm not going to go again over the comparator thing. I'm going to go straight into the Schmitt trigger. Or maybe I'll go back to the comparator because I need to explain the output. Basically, the output is going to be either a low state at 0 volt or a high state at 9 volts. I think I drew something here. Actually, I was looking at that. So if you use it as a comparator, the Vout is here, 0. Low state, it's not actually 0, it's more like 1 point something. And this is when the switch happens. And this is the high state, which is the 9 volt, or more exactly, I think it's 7.5 volts. And this is the input voltage. So this is when you turn that pot. And this low state corresponds to LED 1 being lit, and this high state corresponds to LED 2 being lit. And if you use it as a Schmitt trigger, I'm going to explain it right now because this is the state kind of depends on history. So if you look at this one, here you go from and you'll see on the bench when I do the voltage, the input voltage from 0 to 10, and I turn the knob here, I'm increasing the input voltage, and this behaves like a comparator, but the switch, the voltage for which the switch happens is delayed, so it's here. And then when you go the other way, when you turn the knob the other way, that is when you reduce the input voltage, you don't go back down this way, you go back down that way. So there is like a zone where the state actually depends on history, whether you're coming from the left or coming from the right. And this behavior is called hysteresis. Hysteresis, and it's nicely shown here. Okay, so this is the signal, the input voltage. So when you increase the signal voltage, it's going this way. But when you decrease it, you go from here down to here. Okay, let's go back to the circuit. Yeah, so the LEDs are just a way to see the output state, either low or high. If LED 1 is lit, it's a low state, and if LED 2 is lit, it's the high state. That's all. Okay. Anyway, so up to now, we have always considered a feedback loop that's negative, always connected here. So instead of being there, before it was always here on the negative. The same thing. And so you would have the feedback loop with a resistor, and then you would have another resistor here, and either you would have the signal, the input signal coming in, or you would be connected to ground. But here it's different. Here we are using a positive feedback loop. Positive feedback loop. That's your feedback loop here. And what happens is that this is not good for audio applications, because this is going to drive the saturation even worse than when you don't have a feedback loop. So this is useful for like this kind of circuit where you need like digital or logic, whatever, where you need a signal that's either 0 or 1 and nothing in between. So that's probably the only reason why you would want to use a feedback loop that's positive. And here it's positive. This is that control pot that you will see that when I go to the bench. And okay, then this is your positive feedback loop. This is the output. And if the output is low, or let's say 0, this LED lights up, and if the output is high, let's say 9 volts, this LED lights up. Okay, so let me see what I drew. Yeah, this is the Schmitt trigger, blah blah blah. And I'm just gonna go here because I kind of wrote down the voltages at 69, voltage at 69 and voltage at 67. So 67 is the output voltage with respect to the signal voltage, and this 69 is the non-inverting. So this is the non-inverting input, and V68 is always 4.75. So this is the inverting input. And remember that when you do audio applications, if you have a feedback loop, the two voltages at the input are virtually identical. Not the case here, because here you are using a positive feedback loop. Okay, it's completely different. And as you can see, V68 is completely different from V69. Again, V68 is the negative input, and V69 is the positive input. Okay, so let's go to the bench. So first we're gonna do a key off. So it means that we're gonna do just a straight comparator. And so let's turn it on and let's see what happens. So LED 1, LED 2, that corresponds to the two states, if you will, of the output. So either the output is about 0. Actually it's more than 0, it's probably about 1 volt or something like that. So that's state 1. And the LED 2 is going to be the state 2, when the output is about 9 volt, but actually less than that, maybe 7.5 or 8 or something like that. So those are the two states. So when you turn the control volume, you are changing the input voltage. So at the beginning, so this is 0, LED 1 is on, you turn it, so the input voltage increases. At some point it's going to switch states. Okay, so it has switched state at 5 on the dial, and if you keep going it's going to stay that way. And then if you go backwards, you're going to get the exact same thing. It's going to switch at 5. That's a straight comparator. See? It switches at 5. So the output, as you increase this guy, the input voltage, the output looks like this. Up and up. So this. So whether you go this way or that way, it's the same. The change is at the same input voltage. It doesn't matter. So it's completely symmetric, if you will. Now, if you use the op-amp as a Schmitt trigger, and they tell you in the Radioshack manual to press on the key, but here I'm just gonna short it. Okay, so now the op-amp is used as a Schmitt trigger, and you're gonna see the difference. Okay, so now I'm at 0 and I'm gonna increase the input voltage, and we're gonna look at when it's changing state. So when the LED 2 turns on. So I'm at 4, 5. Okay, it switches around 6, and if you keep going, it stays on this guy. Now, the interesting thing is what happens when you go the other way. So here I'm going back the other way, so I'm decreasing the input voltage. So this is 6. LED 2 is still on. 5. LED 2 is still on. Boom, at about 4.5, it's switching to LED 1. Okay, so let's do it again. It's gonna switch at 6, and if you go the other way, it doesn't switch back at 6, but around 4.5. Yeah. And it's called hysteresis. It's called hysteresis. So if you increase the input voltage, it looks like this. Like that. It's like the old one, so like that. So it goes like this. But then when you go the other way, it doesn't go back here. It goes further and back down. Okay? So it's called hysteresis. And that's the whole idea between the Schmitt trigger. Okay, so let me try to explain that Schmitt trigger business. So if you look at the circuit from before, so this is the input signal coming in here, input signal coming in at the non-inverting input, so the plus. And by the way, the voltage at that non-inverting input, I call it V plus. This is my 4.5 volt, like a reference voltage, which I call V minus, coming in at the inverting input. This is, of course, the power supply. And you have that feedback loop, the positive feedback loop. And you have RB here, and you have RA there. It's exactly what's in the schematics in the Radioshack booklet. Same thing, and this is the output. So what you do, you need to put your math wizard hat on and do some math, a little bit of algebra, I guess. But this is basically voltage divider. This is a voltage divider. So the voltage V out minus V plus is equal to RB over RA plus RB. Again, this is a voltage divider if you look at those two resistors and those two voltages. So V out minus V plus equals this. And V plus, okay, so V plus minus V in is equal to RA divided by the sum times V out minus V in. Voltage divider stuff. And then you have to combine the two. You combine the two. I did all this already. And you can do it yourself. It's very simple. And you get to this. You get to V plus, so this voltage here is equal to RA over RA plus RB V out plus RB over RA plus RB times V in. So V plus is this voltage here. it's important to have it then, because if V plus is greater than 4.5, the output is going to saturate towards the 9 volt, the Vs plus, the V source plus. And if V plus is less than 4.5, the output is going to be going towards saturation the other way, that is towards 0 volts, because here this is grounded. It's not going to be exactly 9 volt or 0 volt, it's probably going to be maybe 8 volts and 1 volt. So the saturation is, it doesn't go all the way to the V source. But anyway, this is the formula. And now let me get the next one. Okay. Again, my formula is here, and I'll even redraw the thing. And here I put the actual value from the Radioshack experiment. RA is 10K, RB is 100K. So the switch will occur when V plus equals 4.5 volts. That's exactly what I was saying earlier. So if you plug in this equation V out equals 0, you're gonna get the V in moving to the right. I call it the I value. If you look here, so this is V in, okay? And this is the V in I. This is when LED 1 is gonna turn off and LED 2 is gonna turn on. So this is the state, the switch of the state of the output, going from low to high. Okay, so this is for this one. So this is V in H. And now, if you put V out equal 9 volts here, you will get the V in, the low. So if you look at this one, you're gonna go this way, go down this way, and this value here is the V in low. So this is V in high, and this is V in low, this one. So what you do is that you just do that. You take your equation and you put V out 0. Again, V plus is 4.5. That gives you a V in high of 4.95 volts. And if you put V out equal 9 volt in your equation, you're going to get the V in low, which is 4.05 volts. So this is 4.05 and this is 4.95. And this is that hysteresis loop. So if the V in, this guy, increases, you're going to take this path. And if V in decreases, you're not gonna get on the same path, you're gonna go further. So it's gonna be the one dashed. So this is the V in H, this is the V in low. Okay, so we are back to that Radioshack circuit. And I just wanted to conclude by saying that what's important about that hysteresis loop, the plane comparator could be very perturbed, I would say, when you have noise. Because when you have the plane comparator, it looks like this. It goes up and here like this. So there's no, this is like infinitesimally small. So if you have noise here, the output is going to switch very rapidly or very randomly between the low state and the high state, between 0 and 1, which is not good. But if you have a Schmitt trigger, so you could have a lot of noise in this zone, so on the signal voltage in this zone, I should say, and it doesn't really affect the output. It's like it's kind of like a latch. In this zone, when you're in this zone, it acts like a latch. So it stays to whatever it was set before you got there. So if you are coming from here, it stays in this zone, it's gonna stay low. But if you are coming from here, in this zone, it's gonna stay high. So it's kind of a latch, kind of circuit. So that Schmitt trigger is good when you have noise, as you can see, as you can imagine. And it's also good when you want to transform a signal that is slowly moving like a sine wave, and you want to transform it into a square wave. And a square wave is has very abrupt changes. It's either low or high. And if that's what you want, then the Schmitt trigger is a great way to get that. Okay, so that's two uses of the Schmitt trigger that I can see, but I'm sure there are more. So anyway, I'm going to stop here, and hope you have now a better understanding of the Schmitt trigger and also the hysteresis loop, which is this thing, the hysteresis loop. Okay, so I'm going to stop now, and I'll see you around. Bye.